part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to discuss the Hall effect.
Consider a conductor to which is applied an electric field in the x direction. There will hence be a current likewise in the x direction. Next, suppose the magnetic field in the positive z direction is applied. A magnetic force acting on the charge carriers causes them to be deflected in the y direction. Buildup of charge gives rise to a transverse electric field. Eventually, the force due to the transverse electric field will balance the force due to the magnetic field. This is called the Hall effect, and it gives rise to a Hall voltage across the conductor.
The Hall effect manifests itself in metals and semiconductors, but it also arises in magnetohydrodynamic systems. However, for the present, I'll just limit the discussion to solids such as metals and semiconductors. A proper treatment of solid-state physics is necessarily quantum mechanical. Nevertheless, it's possible to glean some useful insight into the physics of metals, say, using classical theory. So with that, I'll begin with the Drude model. I'll go over some of the assumptions of the Drude model, also some observations as well, and then I'll present DC conductivity using classical theory and on the way to explaining the Hall effect, and then we'll go into some of the shortcomings of using classical theory as applied to metals, and then also point out some of the observations about semiconductors. Okay, so Drude proposed his model in 1900, 3 years after J.J. Thomson discovered the electron. And he envisioned metals as being composed of electrons, negatively charged electrons, but also reasoning that there were positively charged particles as well. After all, metals are overall electrically neutral. So you have these much heavier positively charged particles. Essentially, those are the ions. And then you also have electrons. Now, an isolated atom is going to have a nucleus, core electrons, and then out here, valence electrons. When you have a bunch of atoms coming together as in a metal, you'll have nuclei, positively charged nuclei, which carry charge Ze, plus Ze, and you'll also have the core electrons, which carry charge minus Z minus Zc times E, and Zc is the charge of the conduction electrons. So these conduction electrons are free to roam throughout the metal. They're the agents responsible in the Drude theory for carrying the current. I just want to emphasize that this picture of what a metal looks like on a microscopic level is not correct. So let me just digress briefly to show the kind of structure that real metals do exhibit.
Metals are crystalline. In crystalline solids, the ions, atoms, or molecules that compose the solid occupy regular sites in a lattice. Consider one cell of a simple cubic lattice, where an atom or an ion occupies each corner of a cube. The element polonium has simple cubic structure. Because crystals have periodic structure, it is a useful idealization to treat the lattice as infinite in extent. Another common crystal structure is body-centered cubic, where an atom or ion occupies the center of a simple cubic cell. Iron and niobium have BCC structure. In a face-centered cubic crystal, an atom or ion occupies each face of the simple cubic cell. Silver, gold, and copper all have FCC structure.
Drude applied the kinetic theory of gases to metals. Now, there are obviously some big differences between metals and a simple gas. I'm going to go ahead and note some assumptions that are made in the Drude model, as well as some observations as well. For starters, metals are far more dense than a simple gas. In order to quantify this, I'm going to go ahead and calculate the density of the conduction electrons. Density of conduction electrons in a metal is equal to Avogadro's number times the mass density divided by the mass number times the number of conduction electrons that each atom contributes. To make this figure a little bit more concrete, I'm going to go ahead and calculate the density of conduction electrons for gold. Avogadro's number is 6.022 times 10 to the 23rd. The mass density of gold is 19.3 grams per cubic centimeter. The mass number of gold is equal to 196.97, and the number of conduction electrons that each gold atom contributes is just 1. We do the math here and convert this over to MKS units. We arrive at a figure of 5.9 times 10 to the 28 conduction electrons per cubic meter. Okay? Now, second observation, in a simple kind of gas, there's only one kind of particle. In metals, you're going to have positively charged ions and negatively charged electrons. In kinetic theory of gases, you assume that a particle travels in a straight line until it undergoes a collision. In the absence of externally applied fields, in other words, in the absence of an externally applied electric field or magnetic field, in the Drude model, it's assumed that electrons also travel in a straight line until they undergo a collision. Okay? Now, there's an additional approximation that has to occur here. After all, electrons are going to experience the fields due to other electrons, and they're going to experience the fields due to the ions. We use the independent electron approximation, and that means that basically we're ignoring the electron-electron interactions. Also going to use the free electron approximation, and that means that we're going to ignore the electron-ion interactions. Okay? And if you do have externally applied fields, then the electrons are just going to move in accordance with Newton's laws. In kinetic theory, it's assumed that the collisions are instantaneous events, and likewise, that assumption is made in the Drude model. And we're going to introduce a new quantity, tau, called the relaxation time or collision time. And basically, 1 over tau is the probability per unit time that a collision occurs. So therefore, the relaxation time tau is, well, let's say you take an electron at random. That means it's going to travel time tau before it undergoes another collision. And conversely, it means that on average, it's also traveled time tau before the last collision. And we're going to assume, too, that the thermal equilibrium of the electrons is achieved only through the mechanism of collisions. Okay? So a lot of assumptions made, a lot of approximations. And in spite of that, for certain metals, this actually leads to somewhat decent results. So in Drude as well, he envisioned the electrons would be roaming around and they bump into the positively charged ions and then get scattered. Now that we've covered the assumptions and observations regarding the Drude model, we're ready to look at the DC conductivity of the metal. So the system in question will just be a piece of wire of length L and cross-sectional area A. I'm going to begin with the most familiar form of Ohm's law, and that is voltage is equal to current times resistance. So the voltage drop across this length of wire is equal to the current that flows through it times the resistance. Another less familiar form relates the electric field to the current density. So the electric field is equal to the resistivity times the current density, and I am using the Greek letter eta for resistivity. Do be aware that many authors, maybe most, use the character rho. I want to relate the resistance to the resistivity. I'm going to observe, first of all, that the voltage drop across this wire is equal to the electric field times the length of the wire. And I'm going to make use of Ohm's law on the left-hand side. That's just equal to current times resistance. And if I replace this electric field with this expression, resistivity times current density times length, that's also equal to resistivity times length. And the current density is just a current per unit area. So therefore, resistance is just equal to the resistivity times the length of the wire divided by the cross-sectional area. So the resistance depends not only on the substance of which the wire is made, but it also depends on the geometry. The longer the piece of the wire, the greater the resistance, and conversely, the greater the cross-sectional area, the smaller the resistance. Okay? I'm going to calculate an expression for the current density. And I'm going to start out by deriving an expression for the amount of charge it passes through this area per unit time. Or I should say the charge it passes through A during the interval of time dt. Okay? Now, this piece of wire has density of conduction electrons N. So amount of charge per unit volume is equal to the current conduction electron density times electric charge times the volume. Okay? So it's passing through a cross-sectional area A, but per unit time, per this, or rather I should say per dt, the electrons are going to advance a distance v times dt. Therefore, the current density is equal to the charge per unit time per unit area. It's just equal to minus ne times velocity. And notice that the current density is in the opposite direction from the velocity. Now I want to derive an expression for v on average. Okay? So let's suppose that an electron has undergone a collision. As a consequence of the electron undergoing a collision, it's going to acquire a velocity v naught. It's going to be scattered in some random direction. But because there's also an electric field that's externally applied, the electron is going to acquire an additional velocity. So let's suppose after some time t after the collision has occurred, the electron will have experienced some force, the charge times the electric field, or actually minus E, the electron charge times the electric field, 4 times t over m. So the electron will require this additional velocity. But since we are talking about random, or rather averages here, the average time is, in fact, just going to be the relaxation time. If you were to take an average over the contribution of both of these, this term is not going to contribute at all, because when the electrons are scattered by the ions, they're scattered in random directions, so that effect is basically just going to be 0. So what you'll find is that there's going to be an average velocity just due to the effect of the electric field, and that's equal to minus the electron charge times the electric field times tau, the relaxation time, divided by m, the mass of the electrons. So therefore, I plug this expression for velocity into here, and this is equal to minus ne times minus e and now we've derived an expression relating the current density to the electric field. That's equal to ne squared tau over m. And this is represented by the character sigma, and that's the conductivity. And the conductivity is equal to 1 over the resistivity. Okay? Now, in order to write down the equations that describe the Hall effect, I need to write down an expression for the momentum. We'll first begin by recalling that the current density is equal to minus the number of electrons per unit volume times the electron charge times the velocity. I'm going to replace this average velocity by the momentum per electron divided by the mass of the electron. I need to write down an expression that illustrates how the momentum per electron evolves in time. So in other words, what is the momentum at some infinitesimal time dt greater than t? Okay? I want to figure out what is the contribution from the two kinds of electrons. There are electrons that don't undergo a collision, in that interval of time dt, and then there are the electrons that do. Now the probability that an electron undergoes a collision in this interval of time is just dt over tau, where tau is the relaxation time. So therefore, the probability that an electron does not undergo a collision is equal to 1 minus dt over tau. I'm going to figure out the contribution from the electrons that don't undergo a collision first. So the fraction of those electrons really is represented by this 1 minus dt over tau times the momentum at time t plus the contribution from those external fields, the external electric and magnetic fields. And then there are going to be higher order terms as well. I'll just write it as higher order. Now I'm going to figure out what is the contribution from the electrons that do undergo a collision in that interval of time. Well, as it turns out, those terms are going to be proportional to at least dt squared. So they're not going to be linear in dt, they're going to be higher order terms. And I'm just going to write it like that because when we take the limit as dt goes to 0, those terms are just going to drop out. I'm going to multiply out the right-hand side. and collect all terms that are higher order than dt, in other words, second order in dt and higher, into just higher order. So it's going to go to 0 anyway, so we'll just collect that together. Subtract p's of t from both sides. And I'm going to divide every term through by dt, and we'll take the limit as dt goes to 0. The derivative of the momentum with respect to time then is just equal to a frictional damping term that arises because of the collisions, and then also the effect of the external fields. And I'm going to use this equation to derive an expression for the current density in terms of the electric field for the Hall effect, okay?
By the Drude model, it's the negatively charged electrons that carry the current. Note that the drift velocity of the electrons is in the direction opposite that of the current. Hence, for the simulation displayed here, the electrons would be deflected in the minus y direction. If the charge carriers were positive instead, then those positively charged particles would also be deflected by the force due to the magnetic field. A Hall voltage would arise, but the opposite side of the conductor would be at higher potential. The Hall experiment provides a means of determining the signs of the charge carriers.
In order to fully describe the Hall effect, not only derive expressions for the x and y components of the current density in terms of the electric field, there are also two additional quantities of interest. One is the magnetoresistance, and that is defined as the ratio of the applied electric field, which is just going to be in the x direction, and the x component of the current density. It's so-called magnetoresistance because included in it is the effect of the magnetic field. There's also the Hall coefficient, and that's defined as the ratio of the transverse field, that is to say the Hall field, and the x component of the current density, and divided by the magnetic field. We are interested in what's going on in steady state. In which case, the derivative of the momentum with respect to time is just equal to 0. Now, I want to write down equations in terms of the current density, not the momentum, not the velocity. So we'll call the current density can be written as minus NE P over M. Therefore, this first term becomes NJ over NE tau. Second term is the external forces, basically the forces applied by the electric field and magnetic field. Basically just the Lorentz force, so this is minus the electron charge times the electric field minus E V cross B, but again, we want to have this in terms. J cross B over N. Multiply through every term by NE tau over M, so get rid of that factor out in front. NE squared tau over N is just the conductivity. I'm going to move the electric field term over to the left-hand side. to solve for the current density in terms of the electric field, I'm going to break this down into x and y components. So write down the x component equation first. X component of J cross B is going to be Jy times B. Remember, B is in the z direction, and that's going to be a plus sign. Write the y component of this equation down. It's sigma e sub y is equal to j sub y. And this time it's going to be a minus sign e tau, and the y component of J cross B is just going to be minus jxb. At this point, it's useful to introduce the cyclotron frequency. And that's defined as the magnitude of the electron charge times the magnetic field over m. And the reason why that's convenient is because then there'll be terms that contain the factor of omega c times tau. This is the dimensionless quantity, and it gives a measure of the strength of the magnetic field. Okay, so let me just label this equation A, the x component equation A, and the y component equation B. I'm going to solve for j sub x and j sub y. So the first order of business is, let's suppose we multiply equation A by omega c tau and add it to equation B. In that case, the j sub x terms are going to drop out, and we'll only be left with j sub y terms. Next, I'm going to take the difference of equation A and equation B, but equation B multiplied through omega c times tau. When I do that, it's going to get rid of the j sub y terms. So j sub y is equal to the conductivity times omega c tau times e sub x plus e sub y, all over 1 plus omega c squared tau squared. J sub x, current density in the x direction, is equal to sigma conductivity times e sub x minus omega c tau times e sub y divided by 1 plus omega squared c tau squared. So in order to calculate the Hall coefficient, remember that occurs when there's no more current flowing in the y direction. So j sub y is equal to 0. you do the math, you'll see that the Hall coefficient only depends on the electron density. It's equal to -1 over the density, or I should say the number of conduction electrons per unit volume times the electric charge. I will say that oftentimes in solid state physics books, it'll be expressed in CGS units, so that actually is going to have an additional factor of C in the denominator. But anyway, in KS, it's just -1 over NE. Okay? Now, as my old solid state physics professor used to say, the proof is in the pudding. How good a value is this? Well, we just calculated the number of electrons per unit volume, or conduction electrons per unit volume for gold. So let's see if this Hall coefficient calculated using this expression is anywhere near the experimental values. And that number was 5.9 times 10 to the 28th conduction electrons per cubic meter, and that 1.602 times 10 to the minus 19th coulombs. Do the math here. This is -1 over, or rather, minus 1.1 times 10 to the minus 10th cubic meters per coulomb. So how good a value is that? Well, experimental values are around -7 times 10 to the minus 9th, or minus 11th cubic meters per coulomb. There's not very good agreement between the calculated Hall coefficient and the experimental accepted value. At least it's in the right ballpark. Experimentally, it is found that the Hall coefficient carries a negative sign, and that's as expected because we've assumed that it's conduction electrons that carry the current. There are certain elements for which there's better agreement between the Hall coefficient and the calculated Hall coefficient and experimental values. However, aluminum presents a conspicuous failure of classical theory. And the reason for that is that the experimentally determined Hall coefficient is off by a factor of 3. Worse for classical theory, the experimentally determined Hall coefficient in fact is positive. Now, if this is positive, that would tend to indicate that it's the charge carriers are positive, not negative. So the answer to that lies in quantum mechanics, can't be answered with classical theory. I also want to point out the magnetoresistance. When Hall initially did his experiment back in the late 19th century, he was unable to verify that the magnetic field affected the resistance of the wire. The reason for that is that the effect is so small. Another point I wanted to make is the Hall coefficient actually does depend on the magnetic field, and it depends on the temperature as well. And when you do experimentally determine RH, that is what you'll find. Now here was a little bit cavalier in stating that the transverse component of the current density vanishes when the Hall field, or the force due to the Hall field, balances the magnetic force. And in fact, this is true strictly only at the edges of the conductor, not in the interior region. There's a very interesting paper in which the authors solved the boundary value problem, and what makes it interesting is that the boundary conditions are very different from what you encounter in textbooks. I have the reference to that paper, as well as other good Hall effect papers listed on the BocaPhysics website. Okay, so generally speaking, the electric field and the current density are at an angle with respect to each other, so calculate the Hall angle, the angle between the electric field and the current density, and just rewrite this equation relating the electric field in terms of current density in a somewhat more convenient form. If I take the dot product of the current density with the electric field, the first term will give me eta times j squared. The second term is going to drop out when I take the dot product of the current density with the cross product of the current density and the magnetic field. But E dot j is just equal to the magnitude of the electric field and magnitude of the current density times cosine of the angle between them, which is just the Hall angle. You can also calculate the cross product of the electric field and the current density. The first term there was going to drop out, j cross j is just 0. And the second term is going to give me bj squared over ne, and that's just equal to ej sine theta h, or sine the Hall angle. If I divide the second equation by the first, that gives me the tangent of the Hall angle, and that is equal to bj squared over little n, where little n is the number of connection electrons per unit volume, times E times resistivity over j squared, but that is just equal to omega c tau, that dimensionless quantity that gives a measure of the strength of the magnetic field. So if the magnetic field is very, very weak, the angle between the electric field and the current density is likewise going to be
small
as well. Okay? I'm going to close out today's lecture with a few words about semiconductors. As I noted, the experimentally determined Hall coefficient is positive for aluminum, and that would seem to indicate that the charge carriers are positive. In fact, it's the electrons behaving as if to suggest the charge carriers are positive, and it really goes back to a question of how the electrons occupy energy levels. So, talking about energy levels, that really is a quantum mechanical explanation. It's convenient to introduce the hole. It's a fictitious particle, and basically, if you want to think of the current as being carried by positive charges, well, you think about the hole as being an absence of the electrons. We've been strictly talking about conductors up till now, but let me just close out with a few words about semiconductors. There are N-type semiconductors. In that case, dominant carriers are electrons. And there are P-type, and the dominant carrier in that case is the hole. Now, silicon is used to make, is used in Hall effect sensors, and these are ubiquitous out in the world. Basically, they make use of the magnetoresistive effect, And they have 3 pins. There's one for pin for the supply voltage. Usually take between 3 volts and 6 volts in a lot of cases. There's a grounding pin, and there's the output voltage. It's the output voltage that depends on the strength of the magnetic field. Okay, and these are used to measure things like the flow rate of water. They're widely used in automotive applications like determining the transmission speed, determining the position of the crankshaft. They're also used in undergraduate physics labs so that students can measure the magnetic field due to things like solenoids, Helmholtz coils, and simple magnets, and sometimes use them to verify Ampere's law. Now, we'll be posting a video on the Learning IoT channel, and that will show you how to use a Raspberry Pi to get magnetic field measurements using a Hall effect sensor. So you'll find a link to that on the learningiot.net website.